Hello everybody. In this video I'm going to demonstrate how to do a multidimensional Rasch analysis using ConQuest. ConQuest is a software that can handle both unidimensional and multidimensional Rasch analysis as well as many facets Rasch analysis. So in this, from this perspective, it's quite flexible and useful. Now this is the interface of ConQuest version 3. Now the latest version is version 5, but I think version 3 and 5 should not have a lot of differences. If you have not installed ConQuest on your machine, you can go to the ConQuest website. I will leave the link of ConQuest website in the comments section of this video, and you can download it from there. You can go to the purchase section and scroll down and click on Acer Shop. So you will be navigated through the website and you will end up here. You can download the 5th version for Windows, and of course it's going to be a 30-day trial, which I think if you are already familiar with the analysis of multidimensional data should be pretty fine. I would also like to add that we have done 2 extensive reviews of Rasch measurement in language assessment, which I assume would be suitable and useful in other fields as well. One is published in language testing just recently, and the other one is more recent and is the a review of item response theory in language testing with focus on dimensionality analysis and its implications for language. Okay, so let's go back to the ConQuest and let's review what kind of inputs we need to include in the analysis to get it run. The first thing that we can observe in this folder is that I have quite a few files here. The 2 most important ones are these. One is the dat file, which includes data, and the other one is the command file, which has an extension of CQC. In order to create this CQC file, you can just create a usual text file like this, and then change this extension of txt into manually to CQC, and just click OK and enter, and it will be fine after that. Now, one of the things that we need to take into account is the content of the command file. This is a 2-dimensional analysis, and it's basically sort of between item multidimensionality, which means that since items 1 to 5 measure 1 dimension, that's dimension 1, and item 2 and items 6 to 10 measure the 2nd dimension, they don't have any overlaps between them. Thus, this is called the case of between item multidimensionality. Sometimes items measure 2 dimensions at a time, or some even more dimensions in some cases. That is called a within item multidimensionality. But I think it's easier to start with a between item multidimensionality because it won't be very time consuming. So I'll leave these descriptions and the command lines in the description box under the video, so you can just copy and paste it into your command file if you want to run a multidimensional Rasch analysis. Remember that we have got 2 dimensions, but what we could do is to include more dimensions. Since my data is binary or dichotomous, so the scores that are going to be used for the analysis are 0, 1. This bracket represents dimension 1, which means that items from 1 to 5 load on the 1st dimension or measure the 1st dimension, and items 6 to 10 load on the 2nd dimension. That's why we've put it into the 2nd bracket. This represents the 1st dimension, this represents the 2nd dimension, then followed by an exclamation mark and followed by items, and the rest of the story. The other thing we need to take into account is that after each line, a command line, except for the title, we need to include a semicolon. Otherwise, we will get some errors from ConQuest, indicating that there's something wrong in the command line. So I think this is pretty good enough for a basic and useful, at the same time effective analysis. So I'm going to close this and close this as well and start running the analysis. In order to run the analysis, first of all, you need to start a new analysis from the file menu. Next, go to Analyze, Command. Go to Command, and from this drop-down menu, choose Data File. So we click on Data File, and you find your data, which in my analysis has been saved as vv.dat. I'm going to click on it and open it. And we need to ensure that our data file has been opened and recognized in the output window, as you can see from here. Let me go back to the folder I had created and explain that the vv.dat file has, let me open it with a notepad, has got around 27 items, if I'm not wrong, in it. However, for the current analysis, I'm asking ConQuest to only look at items 1 to 10. So it's up to you to how many items you want to look at. I think for the analysis I want to carry out, 10 items would be just about enough. In addition to that, remember that there are some other input files here, and actually one more input file, which is .lab. But for the current analysis, it's not going to be used. I've just parked it there because I wanted to show you. And there are two other files called .int and .shw. These will be created automatically because a part of your output will be saved in these two, so don't be worried about it. As a result, the only two important files that you will need for an analysis like the current one will be the CQC file, which includes a command file for the analysis, and also the DAT file. So let's go back to the analysis. Now, in order to open the command file, we need to go to File and Open. No save, don't save changes. Okay, and after opening it, you can find your command file. The name is arbitrary. You can call it anything you like. I've called it 2 dimensions, so I'll remember that my analysis got 2 dimensions. And open. At this point, what we need to do is just to run the command. You click on the Run button there, and you can click on Run All or select some part of the command below and run it. But for the analysis that I'm carrying out, I'm going to click on Run All. What we expect to see after this stage is iterations. It's going to take some time for iterations to converge, but don't worry, you can wait for it, and I hope your computer is fast enough, because my computer is not really that fast. So it's going to take some time. I'm going to pause the video as the iteration is ongoing. So iteration started. As you can see, it's still ongoing. It's around iteration 150 something. We should wait for the convergence of iterations. Okay, so now it's computing empirical errors, meaning the iteration has ended and errors are now being computed. Okay, I got this error message, but it's fine. It's not a kind of fatal error, because it says that the output file, the SHW file, cannot be opened, but that's fine. You can just click OK. And your analysis has been carried out. The mean score of the first dimension is minus 0.88396, and the mean score of the second dimension is minus 0.27030, which indicates that the first dimension is easier to score on compared with the second one, which is more difficult to score on. But the differences is not that big. We also notice that the correlation between the two dimensions is very high, and that's 0.0 9261, which is really high, and it indicates that the two dimensions are probably the same, or they should be estimated together as one dimension. I'm not surprised to see this because the test that I'm examining now is an English test, which is supposed to be a unidimensional test, but for the sake of presentation and illustration, I have assumed that there are two dimensions underlying it. So these are the first two basic pieces of information that we need to look into. Now we can take a look at the tables. For example, we can look at the summary table, you can look at parameter estimates, etc. Let's start from, let's take a look at the summary table. And this is the summary of the analysis. I'm not going to go through it because, you know, it's like the sample size is just 1,000, etc. Oh, one more thing is the final deviance. The deviance is a fit statistics, a global fit statistics. It's useful when you're doing model comparisons. So if I had run a three dimension model and a one-dimension model, I could have looked at the deviances of the three models and could have chosen the best one according to the deviance. The smaller the deviance, the better the model. So for the time being, it's not of much use because I don't have other models to compare against. I can go to item parameter estimates, etc. Let's take a look at the item parameter estimates. The estimates are here on this column. For item 1, the estimate is 0.2118 with a standard error of measurement of 0.072, which is not too bad, which indicates that the actual estimate of this parameter would fall between 0.218 plus minus this amount of error. Now there is another section, or another block by the name of unweighted fit and weighted fit. Weighted fit is outfit in traditional Rasch analysis, and unweighted is infit. We look at the mean square values, and I have discussed this in quite a few other videos in Rasch analysis. They're going to be interpreted in more or less the same way. But in addition to what I have already presented in other videos, you see that we have got confidence intervals, which makes the interpretation of the fit statistics quite easy. We would expect that the mean square value in this column would fall between 0.91 and 1.09. That's a confidence interval. Now, if it does not fall between these two, then the t-value, which is similar to the z-standardized fit statistics in unidimensional Rasch analysis, would get inflated, which would mean that in certain cases, like for example this item, as item number 4, we have a statistically significant deviation from what is expected. So a fit value of 1.22, although it seems to be fine, is actually deviating significantly from the expectations of Rasch measurement because the t-value is pretty high. And how do we know that? Because it doesn't fall between the confidence interval of 0.91 and 1.09. Therefore, this is a misfit, and the misfit is statistically significant. However, we also know that the t-values or z-standardized statistics in Rasch analysis when it comes to fit are extremely sensitive to sample size. Therefore, since our sample size is pretty large, about 1,000 plus, I think we should take this with a pinch of salt and do not jump the gun and do not claim that this is absolutely a misfit. I think to me this is not really too much a deviation from the usual 0.8, 1.20 sort of a range which is considered for multiple choice questions. So you can interpret the t-value with some caution. Okay, let's go back to this side. So it's a good idea to go to tables and to click show. So you can get all sort of parameter that you need for your analysis. In this analysis, I only need these. I don't. Let me see. I don't really need the rest of these statistics because that will just give me enough information. What I would like to do though is to look at the MLE, that's maximum likelihood estimation, which is commonly used in Rasch measurement. If you like, you can also choose, for example, WLE or weighted likelihood estimates. So let's just click OK, and all of these, the information that will be necessary will be outputted for me. Let me drag it a little bit to the left hand side. I'm going to scroll up. Yes, the correlation has been outputted again, and the reliability statistics of the first dimension versus the second dimension can be seen here. For the maximum likelihood estimate, the reliability estimate is 0.333, whereas for dimension 1, whereas that for dimension 2 is 0.366. So the second dimension has a slightly higher reliability estimate. It's interesting that the traditional Chromebox Alpha is pretty high. It's 0.723 and 0.3006. 706. That's one of the differences between the two reliability statistics. If you scroll down, you will see the conventional Rasch right map. In this case, the right map has it consists of two dimensions, 1 and 2 from the top, and also the items. So this is the estimate of the ability of people on the second dimension, which looks like a sort of normal distribution. And this is the estimate and the distribution of the ability level of people on this first dimension, which is also somehow like a normal distribution, but they have different mean scores, as discussed earlier. And these are the distribution of items. So item 6 is the most difficult one among all of the items to score highly on, whereas item 7 is the easiest one to score highly on. In addition to that, you can get quite a few other useful statistics, like item parameter statistics, as I showed before. And then what else would be useful here? Well, we've already gotten this combined item difficulty map, because the menu can show you a lot of information that's already separated under the menu. What I would like to do is now to go to plot. In plots, you can, for example, get the item characteristic curve. So let's get the characteristic curve by score. Click, and you can either get the characteristic curve for all items or choose some items, for example, these two, etc. But for the time being, I would like to get the characteristic curve for all items. And I would like to get the maximum likelihood estimate. And click OK. If you're interested, you can actually save the plots, all of the plots for all of the items, as separate PNG files now or later. Okay, so the item characteristic curve for item number 10 has been outputted. Let's start from item 1. Okay, this is item 1. There are two lines here. One is the ogive curve, which is the expectations of the Rasch measurement, and the other one is this is solid. And the other one is dotted line. The dotted line represents the actual ability and the distribution of the ability of test takers in item 1. Okay, so the mean square value, the weighted mean square value, which is the outfit, is 0.94. There's a little bit of anomaly here, because as you see on the horizontal line, we've got latent trait in logits. That's the estimated ability of students. And since the latent trait estimate for these two groups of students is the same, but their probability of answering the items, as you see as represented on the vertical line, is different, then I'm afraid we're looking at a problem here. Now, it could result in some degrees of misfit, but it seems that in this case misfit is not that high as indicated by the mean square values. Now for item 2, as you see, there is a tighter consistency with what the Rasch measurement expects. So this is not too bad really, and the weighted mean square value is pretty much close to the expected value, which is 1, but we have got two anomalies interestingly here and here. Each dot represents groups of test takers, not just one person. And for the third item, you can see things change. Another thing that we need to pay attention to is that the ogive curve here changes two things: the slope and the intercept at the same time. The intercept is right this point. In Rasch measurement, the unidimensional Rasch measurement, the intercept should not change, because intercept in IRT analysis represents item discrimination, which is fixed in Rasch analysis, and therefore we could say that a multidimensional Rasch analysis is something between one parameter logistic IRT and two parameter logistic IRT, given the fact that the discrimination parameter or the intercept changes as you go through the items. So I'm going to quickly go through the items and perhaps pay attention to this point and see how the discrimination or the intercept changes as we go through the items. As you can see, different intercepts for different items. That's one of the things we need to take into account. Okay, I'm going to close this. I'm going to go back to plots and cumulative item characteristic curves, again for all items, and again I'm going to use MLE and click OK. There we go. It's basically similar to what I already gotten. What I would like to add here is that you can basically save this as a PNG or a PMP, or you can change the color if you like. You can click on this and change the color, for example, background into, let's say, blue, and you'll get a blue one, but it's not very visibility is not very friendly for eyes, so I'm going to go back to the menu and choose white again, and there we are, and close this. Let me see if you can get a test characteristic curve as well. Of course, this is a multidimensional analysis. I'm not sure if you can output it, but let's click. Let me see if we can get it. Oh yeah, we cannot get it actually. This is multidimensional analysis. So for multidimensional analysis, I think we can't get test information and item information and test characteristic curve, but we can get right maps. Actually, they're very useful. There we are. And let's click maximum likelihood estimate. And click OK. Yeah, okay, so we got this. This is the distribution of people. There should be a line connecting these dots, and I think if we get the plausible values, maybe we can get that line. Oh yeah, okay, we got the line here. This is easier to read. So for dimension 2, as you see on this on the right hand side, the distribution of people is like this. It's pretty similar to the conventional right map which we looked at, and the distribution of items in terms of the difficulty level is like this. So let me draw a line here for you around them, so you can see that this is how the items have been distributed for section 4 dimension 2. How about dimension 1? Let's go back to this part and look at dimension 1. As you see, the distribution is like this. It's not as smooth as what we saw for dimension 2, and the items shift their position a little bit. Let me just toggle between them. 1, 2. Okay, so it seems that it gives me both plausible value distribution. This is a plausible value distribution, and also maximum likelihood distribution at the same time. What I can do is just really to close everything and go back to plots, so we can only get plausible values. That seems to be easier to read. Yeah, plausible values. This is for dimension 2, as I mentioned just earlier, and this is for dimension 1. So the distribution of items is not that widespread in terms of their logits. This is the logit line here. So they are kind of clustering around 0, and they're not deviating that much from 0, which could be a reason why the reliability statistics were pretty low. And for dimension 2, they're also clustering around 0, because this is the line of 0, and they're just around 0. Then I would assume that in a better measurement there will be a widespread range of difficulty for items. Some items would fall on top, some items in the middle, and some items are at the bottom. So there will be a less error of measurement and higher reliability statistics in the analysis. Okay, so this is how you can represent it. Overall, I would say that the analysis indicates that it's a better idea to go for a unidimensional Rasch analysis, given that there was a high correlation between the two parameters, the two dimensions. So and that was indicated by the correlation of 0.926, if you recall. And this is how you basically can run a multidimensional Rasch analysis. You can expand this, and for example, if you've got a questionnaire with several dimensions, in the same way you can run the analysis and look at the fit values and other parameters of Rasch measurement, etc. Okay, this brings me to the end of this video. Thank you very, very much for your attention, and have a wonderful day.